Now, lecture 7.8 deals with the differences between a one and a two-tailed test. And one thing that will help you is to keep in mind that when I discuss one-tailed or two-tailed test, I'm referring to the idea that we have a critical region that's confined to just one tail. So in this case, I'd be looking for a decrease. And in this case, I'd be testing for an increase. We went over this before when we talked about the significance levels. One-tailed tests whether or not there's an increase or a decrease compared to some standard. So this could be applied to any of the techniques that we've learned about in our testing of mean differences. The whole idea is that alpha, or our significance level, is concentrated either at the top of the distribution in the case that I'm looking for an increase, or at the bottom of the distribution in the case that I'm looking for a decrease. Whereas two-tailed test, as we went over before, divides alpha evenly among these two areas. So this is going to be alpha divided by 2, and this is going to be alpha divided by 2. That looks more like sigma, excuse me, by 2. Whereas this is going to be alpha, and this is going to be alpha. Okay? So the difference between a one and a two-tailed test refers to the direction of your hypothesis. If you think that a certain training procedure will increase productivity, then you're dealing with a one-tailed test with a positive critical value. If instead you're testing that an intervention will reduce error rates, then you've got a one-tailed test and you're going to have a negative critical value. But if instead you're just looking for, does leadership training affect employee morale, and you're not hypothesizing an increase or a decrease, then you have a two-tailed test and you're going to divide your alpha level among those two values. These realities are reflected also in the expression of your hypothesis tests. So in a null hypothesis case, when we have a two-tailed test, we're testing whether or not the two groups are equal. So we have mu1 is equal to mu2, or we have mu1 is not equal to mu2 in the research case. For a null hypothesis situation in which we're testing whether or not there's an increase from time 1 to time 2, it always makes sense to write the research hypothesis first, to the extent that this is our group before training, and this is our group after training. The research hypothesis suggests that training increases performance, whereas the null hypothesis is going to express the opposite. As we see this in the context of the curve, this is exactly what we were talking about before. Remember that with hypotheses, we're asking whether or not an observed difference is statistically significant. And our decision rules refer to this idea of where are t computed. I've called this the t ratio in previous slides. If the t ratio is included in this area, then we reject the null. But if the t ratio is in this kind of non-shaded area, then our decision is to retain the null. So in a one-tailed case, I have all of alpha at the bottom end or at the top end, depending on whether I'm dealing with a one-tailed left side test or a one-tailed right side test. But in a two-tailed case, I have both tails of the distribution represented.